Assalamualaikum. Good morning. Can you hear me?
Morning, doctor. Yes, can hear.
Assalamualaikum, Dr. Aswika.
Okay. Thank you guys for joining me for today's lecture. Okay. After we gone through the P controller, PI controller, PD controller, and PID controller. Now we are going to move to the one of the critical and important tasks of using a PID controller, which is the tuning method. Okay, so tuning method basically is to choose the right values for the KP, KI, and KD, the proportional values, the integrate values, and the derivative values. Because as you know that PID controller is the controller that will fasten the transient response and reduce the steady state error to zero simultaneously. Okay, so it have two tasks together must be performed in order to achieve the spec design stated in the problem. The spec design or the specification design usually mentioned in overshoot percentage, which will give you the zeta values automatically. And then the peak time, okay, the rise time, the settling time, especially, so that the system can achieve faster or quicker settling time, okay, to settle the response. So in order to do that, we must use a PID controller, okay, which is worldwide use in industry in digital form, okay, as I show you in the picture previously. So even though the digital PID controller is in the digital form where you have a hardware connected to the process, the important thing is for the engineers is to calculate, to plan accordingly to fulfill the spec design stated in the target of the control parameters. So that's why you have to choose the right KP, KI, and KD. The technicians, the technical assistants, even the workers, they don't know how to choose the right KP, KI, and KD. Okay, what they do is based on the experience methods, okay, and then try and error, which is not good in terms of working practice as an engineer. So as a young engineer like you all, so you must have the knowledge to tune the PID controller so that you can come out the right values of KP, KI, and KD, assign these values to the technician or the technical assistant, and they will key in to the PID controller so that we can control the system, okay, or any system under control. So we have several methods for PID tuning controller, okay, as stated here. If you go Google, you have a ZN, okay, one of the method. Then Cohen, okay, one of the method. Then you have a method of CHR, okay, okay, and a lot of names, okay, which you can Google in your laptop or in your computer. So the PID controller, widely used in the industries in which the KP, KI, and KD parameters can often be easily adjusted. Okay, so since this K is the gain value, okay, or it is used one important device in electrical and electronics. We call it as a potentiometer, okay, or variable resistor potentiometer. Okay, so this is behind the knob of the controllers is this circuit, which is you vary the gain from the minimum to the maximum. Maybe the minimum is 0, then the maximum is 50. So you adjust the knob, okay, of the KP, KI, and KD in order to achieve the right gain values. So the tuning generally involve the choosing of the correct parameters KP, KI, and KD. Okay. So the choice of method depends on whether the control loop can be taken offline and on the response time needed for the system. So that's why before you tune the PID controller, you must know the mathematical model or the transfer function of the system under control. Okay, let's say the system is a system that like a motor, for example. Okay, so DC motor, we know that DC motor is a second order system. Okay, if we neglect or ignore the value of inductance. But if the inductance value is significant, is a big value, so the DC motor become third order system. Okay, so whatever it is, you must have the right model of the DC motor, either second order or first order. So you have the numbers of the transfer function, you have the coefficient values, and then you put it inside your computer program and you simulate first, okay, using the KP, KI, and KD before you insert the value in the real hardware. So this is what I call as offline. Okay, offline meaning you do the simulation first and see the response at your laptop or at your computer. After it satisfies you, so now we can tune in or insert the KP, KI, and KD value to the PID controller, okay, in the real hardware. Then you measure, okay, on the DC motor, which is second or third order, and you can monitor it using oscilloscope, or you interface with your laptop that can display the input and output signals and show the error as well. So this, when you implement it like this, it will be online, okay, like us now is online. Okay, so online meaning face to face with you through the computer using a Zoom platform. Okay, so online. But if I recorded my lecture and then in the studio alone, then after I finish my lecture, I give the MP4 or the link of the YouTube to you, so that is become offline class. Okay, which is a recorded video. So this matter very important. Before you key in online, you simulate the PID controller using offline first and see the response. What do you call that as the estimated response, or the what do you call that expecting results from the offline, which can build up confidence on you when you key in using online. So that's why, as I told you before, method of tunings is a lot in the listing in the Google, but I took 4 methods, which is manual tuning, Ziggler-Nichols method, software tools, and Cohen. Okay, so each method have their own advantage and drawbacks or disadvantage. Okay, for example, for manual tuning, okay, so manual tuning is based on experience. Okay, maybe the workers have 3-decade or 4-decade experience, okay, to control that particular process or plant. So they just use their hand and they estimate, okay, without any mathematics background, no mathematics calculations. So this one not required, okay. Then the disadvantage is require experienced personnel. So meaning that the person that do the manual tuning must be really experienced worker, okay, or at least 10 years or 20 years experience. If we send new graduates from UTM to do this, so I'm quite worried that they don't know anything, okay, they cannot blend the knowledge of the PID controller, so they will destroy the system totally, including the system and the controller. And then the other methods which is included in the syllabus is known as Ziggler-Nichols, which was introduced in 1942. Okay, Ziggler-Nichols is the name of person that invent this method. Is a proven method. Okay, established method, can be applied online. Okay, can be applied online and offline. And the process upset some trial and error. It is a very aggressive tuning. Okay, very aggressive tuning. The other method is software tools. Okay, this is provided by the software of the company that provide the system. Okay, they come out with a software that can control the system. So this one, the advantage of using these software tools provided by the manufacturer is consistent tuning. Is online, it can be applied online and offline, and is various techniques can be applied. For example, is a national instrument, one of the provider of the instrumentation and control system. So they have the computer program, which in the software tools using object-oriented programming. Okay, and the drawbacks of these software tools is it is very expensive. Okay, very expensive because they are using a license. Okay, it needs some cost. You need money. Okay, FUA'AD, no software tools. Okay, so that's why, and also the workers need some training. Okay, so they will send for 2 months or 3 months training, maybe in Malaysia or in overseas, in order to understand the software tools and the process that is relevant to the software tools. The other method is known as Cohen, which is introduced in 1953. This one is not suitable for dynamic system. Dynamic system meaning DC motor, AC motor, something that is dynamic, something that is rotating or moving. Okay, so Cohen is usually good for process system, process models. Okay, process meaning that, for example, food industry, what else? Pharmaceutical industry, oil and gas. This is a process. Okay, process industry that using a process control. Okay, and it needs some mathematics a little bit. Then can be applied. Cannot apply offline. Okay, is online and is good for first order process. Okay, but when it goes to the higher order system, so Cohen is not suitable anymore to be applied. So far, okay?
Yes, doctor.
Okay.
Doctor, one question. What does it mean for the Ziggler-Nichols, right? What does it mean by very aggressive tuning?
Aggressive tuning meaning that it calculates very fast calculations, then you get the value, Kp, Ki, and Kd. The time to calculate is it's not long, it's very short, and then a few seconds you get the value of Kp, Ki, and Kd.
And how about process upset, doctor?
Process upset is something which is involved in the process industry. Okay, for example, food industry, pharmaceutical industry. This is a very slow process.
Slow
Okay.
process.
slow process, meaning that if you want to produce, for example, a food, okay, from a process, there is a batch process. So usually for process, they're using programmable logic controller, batch by batch. First is the raw materials, then they process the raw materials, and then they put some sugar, then they put some salt, okay, and then they dry. So it's a batch. After finish one batch, then go to the another batch process, then go to the other process until the final product, which is the what do you call that, packaging, okay, and sent to the for export or import. So several methods for tuning a PID controller. Okay, sorry. The following table summarize the effects when the parameters are tuned manually. Okay, as I told you before, manually is without any mathematical background, no control system background. Okay, they just tune it. Okay, so it will effects of increasing parameter independently. Okay, for example, so if you tune KP, okay, the rise time will be decreased. The settling time have a small change, and the overshoot can be increased if you increase the gain. Okay, steady state will be decreased, and stability will be degrade, meaning that it's not satisfied at all if you're using KP. So KI, when you tune KI, rise time will be decreased, settling time will be increased, overshoot percentage will be increased, steady state error will be eliminated totally because we are using integral. Then the stability also will be degraded. Okay. But when you use KD, the rise time have a minor change, the settle time will be decreased, overshoot percentage will be decreased, the steady state error no effect, okay, in the theory, and it improve stability if KD is a small value rather than a big value. Okay, so this is the effect when you use the PID tuning in a manual method. So this method is used when the system's Ziggler-Nichols method used when the system model cannot or difficult to be obtained, okay, either in the form of differential equation or transfer functions. Okay, so Ziggler-Nichols introduced an effective method for the parameters adjustment by using the method which is known as the alternate cycle method. Okay, so Ziggler-Nichols using this method. Okay, so they have a cycling of signals that we calculate in order to find the KP and KD and KI value. So in order to do the alternate cycle method for Ziggler-Nichols PID tuning, so there is a step for it. Okay, so the first step is you set the KD equal to KI equal to 0, which means that you minimize the effect of derivations and integrations. Okay, first you set KD equal to KI equal to 0. Why? The purpose is to minimize the effect of derivation factor and the integration factor. Number 2 is to increase the KP gain until the system reach critically stable, okay, and oscillate. Okay, oscillate itu maknanya dia berayun, okay, like a sine wave oscillate. So, which will the truth behind it is when the closed loop poles located at the imaginary axis. Okay, so it means that we want to find the critical gain, okay, KC. So when the root locus cross the imaginary axis, the intersection point between the root locus and the imaginary axis is known as a point which produce critical gain or KC. And then obtain the gain which is known as KU, KC or KU. Okay, some books refer as KC, some books refer as KU, and the oscillation frequency which is omega U. Okay, so in some book they are using KC and then B omega n. But for the purpose of Ziggler-Nichols method, the point that intersection between the root locus and the imaginary axis will produce a critical gain, which is known as Ku, and the oscillation frequency for the critical gain is known as omega u in radian per second, okay, or Tu at that particular time, okay, which is the period, okay. And then you calculate the Kp gain, okay, Kp gain that is supposedly needed using a formula. So in order to do Ziggler-Nichols tuning, so you must have a standard formula, which is shown here, if I'm not mistaken. This table, okay. So let me finish first this one. So based on the required type of controller, calculate the necessary gain using the formulas in the table. So this is a table that will be provided during the test and the exams, okay. So it is from a book, okay. So the controller is P, PI, and PID, okay. So since we are using a PID, so we refer to this for Kp is equal to 0.6 multiplied by Ku. Ti, the period of integral, which is equal to Tu divided by 2. And Td, okay, Td, which is equal to Tu divided by n, okay. So note that Tu is 2 pi divided by omega u. Okay, so how do we get omega u? Omega u is the frequency at the critical gain. How do we get the critical gain? Ku. Ku is the gain where the root locus intersection with the imaginary axis in the root locus plot. So you obtain Ku, you will obtain omega u. After you obtain omega u, so you will get Tu. And this Tu will be, Tu and Ku will be used in the Kp value, Ti value, and the Td value. Okay. So the the formula of the PID controller is GPID is equal to Kp 1 over 1 plus 1 over TIS plus TDS. Okay. Or this one is based on the table, but this another form which is I wrote already in the previous lecture last week. GPID is equal to Kp plus Ki over S plus Kd over S. So both can be used, okay? So from here, okay, which is if we simplify, so it will become Kd, it will become S squared plus Kp divided by Kd is a ratio for the S, and then Ki over Kd. Okay. Example 7. Okay. Raja Ahmad Zahid. Raja Ahmad Zahid. Hello, Raja. Sleeping. Azira Ahmad.
Yes, doctor.
Can you read the question, please? Example 7.
Design a PID controller for unity feedback system with the open loop system, which is given as GS K300 over S square plus 30S plus 100.
Thank you very much. Okay. So the answer is given. Okay, the answer is given. Okay, so PID controller. Unity feedback, okay, with the open loop system is given as this. So you can draw the, okay, PID, okay, cascaded with the GS, which is given, okay. So this is your input, this is your output, and it is a negative feedback, okay. So this is the block diagram for this particular problems. So we have a 300K or K300. This is multiplications. S over S square plus 30S plus 100. Okay. So what we know about this? What information we can get from GS in terms of order of the system? Azizun? Azizun? Ido?
Yes.
What is the order of the system? Third order. Okay. Yeah, multiply this one, you get S cubic kan?
Yes. Okay. Third.
Sun Yi Teo. Sun,
Yes, doctor.
matahari. What is the system type?
One.
Type 1. Because we have the poles at the origin. Okay, so this is the answer. But anyway, the answer needs solutions. So the solution is first with this 300K divided by S square (100). Okay, so we have to draw the root locus. Okay, so from the root locus, the highest order is 3. Okay, so 3 root locus paths, right? You have one blue. This is the zeros. Okay. This one is, I'm not sure this one. Can somebody help me find the roots of this? 30S plus 100. Somebody help me? The roots for this?
Hello.
Negative 3.82.
Negative 3.82.
And
Negative 20 and negative 26.18.
18. Okay, so that is the open loop poles. Okay, open loop pole, ni Umar.
yes, doctor.
This one is open loop poles or closed loop poles?
Closed loop poles.
Yes.
Right.
Sadenan sakit, yeah. Right.
Okay.
Sadenan sakit. Sadenan sakit.
Yes, doctor.
Minus 26.18 is open loop poles or closed loop poles?
We should have to divide it using the real part.
Sadenan sakit.
Yes, doctor.
Kamu sabar.
May I know the dominant pole here?
Minus 26.18 is open loop poles. Okay.
Oh, okay. Doctor, we should have to compare it using the ratio, right?
No. We are
Oh,
about the ratio now. We are talking about the difference of closed loopholes and open loopholes in the root locus plot.
okay, Doctor, I understand.
One more question. This is what? Kerengan sakit.
This is the point, Doctor, where gain equals to 0.
No. This one. The point that can you see?
Okay, the breakaway point.
Breakaway.
Yes.
Breakaway. So the breakaway point is open loopholes or closed loopholes?
Closed loop poles.
Closed loopholes, because it's on the root locus plot.
Yes.
Understand,
Okay.
everyone? Okay, so I leave it first. Okay. So you have a root path 1, path 2, ended at infinity, ended at infinity. This one ended at infinity. Okay. This one without controller. Okay. Without controller. Then we find the time response of this. Okay. So the time response is based on closed loop transfer function. Okay. GS 1 plus GS. Okay. Which is closed loopnya. Nurliana Izzati.
Yes, Doctor.
Closed loop.
300K over S square plus 30S plus 100 plus 300K.
So this is closed loop. Okay, so you assume K equal to 1. Okay, and then you inject the 1 volt step. Okay. 1 volt step. And then you obtain this response without a controller. Okay. So from this graph, okay, Nur Aina Shafika,
Yes,
what is the peak time?
1.11 second.
Aina Nabila,
Yes, Doctor.
what is the settling time?
2.45 seconds.
Okay. So we obtain the value and then the and what is the steady state error? Telpel again.
So is the steady state error 0 because the final value is 1?
Yeah.
And
So
if we get steady state error with what the 1 minus the final value, so would it be 0?
yeah. Okay. 0. Right. Thank you. Then we apply the Ziggler-Nichols, the ultimate cycle method. Okay. First step, assume Ki, Kd equal to 0. Okay. Why?
Because it's in the step
Muhammad
to
Shafiq.
minimize the effect of derivation and integration.
Thank you, Nick. I'm asking Muhammad Shafiq. Muhammad Shafiq. Why? Shafiq, are you sleeping? Sleeping, eh? Tak datang. Haikal, why we assume Kp, Ki, and Kd equal to 0? Haikal, tak datang. Safwan, Safwan, tak datang. Abdul Rahman, Abdul Rahman. Tak. Alisha. Alisha,
Yes, Doctor.
why we assume Ki and Kd equal to 0?
Steady state error 0.
Astagfirullah. Alah tu. Ali Imran.
Ya, Doktor.
Why we assume Ki equal to Kd equal to 0?
I'm not really sure, Doktor. Sorry.
Astagfirullah. Tadi baru cakap hidup. Ammar. Ammar.
Yes, Doctor.
Why?
To minimize something. Saya ingat ayat dia. Saya ingat to minimize, tapi tak ingat dah selepas tu.
To minimize and avoid the derivative factor and integration factor.
Itu.
Tak tahu pula. Nak cakap. Step number 2 is to find the closed loop transfer function from the open loop. Macam tadi tu yang Alisha cakap tu. Siapa yang cakap ni? Lupa saya. 300 given. This is given, kan? Given in the question 300K kan. Jadi K tu actually the K is KP is a gain. Controller ni is a proportional gain. So 300 KP over S square plus 30S plus 100. Okay. So actually we have 3 real poles. There is no imaginary or there is no complex conjugate poles. Okay. All are real poles. Real poles. Okay. Then we find the closed loop. Okay. So it becomes 300 KP over S divided by S square plus 30S plus 100. Okay. Plus 300 KP. Okay. Then we simplify this one. Simplify. We open the equations. So it will become S cubic 30S square plus 100S plus 300 KP. Okay. Everybody okay?
Yes, Doctor.
Okay. Step number 3. So from the closed loop transfer function here, if we equate this to 0, it will become
Characteristic
characteristic
equation.
Can everybody say characteristic equation?
Characteristic equation.
There is the equation.
And here from the girls, and Nisa, characteristic equation.
Characteristic
equation.
Characteristic. CHEREQUAN. Then step 3 is from the characteristic equations, we use the coefficient values, which is here 1, 30, 100, and 300 kp. Okay, so we insert into the, what is the name of this table?
Ruth-Lewis.
The Ruth-Lewis table. In order to find the Ku and omega U, kan? Or K critical and omega critical. So S cubic, S square, S plus 1, and S power 0. Insert the coefficient value 1, 30, 100, 300 kp. And then you have to fill up this one, and you have to fill out this one. Okay, this one is 0. Okay. Understand?
Doctor, how we come out with the value for the S1?
S power of 1.
S power of 1.
Siapa tanya tu?
Edwin.
Evelyn Bagus tu soalan tu. Tapi sebenarnya that question is actually the basic question. How we find 100 minus 10 kp? Our brothers don't understand.
Delta
Huh?
negative, that's a formula.
Formula, what is it?
Negative determinant.
Negative determinant 30.
One, not 130, 100. Right? No.
130, kan?
Yes.
And 100, 300. Adrian Justin.
Yes.
Simplify this.
300, yes, minus 3,000.
Okay. Okay. Then you will get this value. Okay. Baik.
Boleh.
Is the control one theory. Right. So and then in Rothwist, okay. In Rothwist, we have a first column and second column. Okay. So this is what I call a first column. Okay. Our concern in Rothwist is first column, right? So the first column stated that one is positive, and so must be positive. Okay, 30 positive, and this one 100 minus 10 kp must greater than 0. Okay, including 300 kp must greater than 0. So we have two equations. Okay, so I read it here. Okay, 100 minus 10 kp greater than 0. Okay, so minus 10 kp minus 100. So since this is a negative, in order to remove the negative, we have to change the sign. So kp less than 10. Okay. Then 300 kp, the second equation, which is this one, is greater than 0, then kp is greater than 0. So that's why the range of stability, this is what I call as the range of stability, is 0, okay, 0, less than kp, less than 10. This is the range of stability. Okay, so I want to ask Arab brothers, okay, Yosef.
Yes, doctor.
If kp is equal to 5, system is stable or not?
It's area. Yes.
Nah.
It's bigger than 0 and less than 10.
Stable or not stable?
Stable. Stable.
Stable. Stable. Correct. Okay. Where is all Arab brothers sleeping? I don't see any list here. Asim Jamil.
Yes, doctor.
Kp is equal to 11. Stable or not?
Not stable because it's not between 0 and 10.
Shukran. Oh, khairan.
You too.
Only two Arab brothers over here. The rest is sleeping. Aru A17 KE5135. Who is this? Aru A17 KE5135. Nobody.
Doctor.
Who is that? Aru? Aru
Arunab. ARUNABH.
Arumugam. What's your name?
Arunab.
Aruna. You are from?
Bangladesh, doctor.
Bangladesh. Yamunasin. Aruna.
Yes.
Yamunasin.
Sorry?
Yamunasin. Speaking Bengali to you. Yamunasin. You talk Urdu.
No, I speak Bengali and English, but I didn't understand you.
Oh, okay. Never mind. So KP is equal to 10. Is it stable or not stable?
It's unstable.
Are you sure?
It has to be less than 10. The range is from 0 to 10.
I'm asking you, KP is equal to 10. Is it stable, not stable?
Not stable.
Not stable. I'm afraid your answer is wrong.
Really?
Lo Jotian,
Yes, doctor.
KP is equal to 10. Stable or not stable?
Stable.
Your answer is wrong.
Oh, not stable.
Oh, Zhenghan, KP is equal to 10. System stable or not stable?
Critically stable.
Good, very good.
It's not in the option.
10 is marginal stable, critical stable, where the critical gain occurred over there. Understand? Hello? Do you understand?
Yes, doctor.
So you must find the range. You must understand these mathematics equations. Because some of the Malaysian, they don't understand mathematics. Even a simple percentage. The Pfizer vaccines, COVID-19, 95%, 95% apa? 95%?
Kasi.
Vaccine, 95%, meaning that 95% will cure. So what is the remaining percentage of not cure?
5%.
Okay. So recently, those who get the vaccine is 450,000. Am I right? Total who have injection vaccines. Am I right?
Yeah.
Okay. And how many people have vaccinated and then they have the COVID for the second time? How many? 40, isn't it? According to the news.
Yes.
So 40 divided by 450,000 multiplied by 100%. So how many percent? 40 divided by 450,000.
About 0.8%, 0.008%. 0.008.
0.008%. So is it far away from 5%?
Yeah.
It's small, isn't it? Still small, isn't it? Majority cure, isn't it? So
Yes.
fraction of Malaysian, they don't understand mathematics. They don't want to learn. Okay, even a simple thing like this. Okay, and then they are key warrior. They talk in the media social. They say that they understand the figures. Okay, so we as the university student, so we must understand and explain to those who are, they don't understand mathematics simple percentage. So 95% cure, 5% maybe there's not cure, but recently we have 40 cases who have been vaccinated out of 450,000, which is 0.008%. Okay, so that's why I insist this, the value of KP. Okay, so that students understand. The range, the value of KP is inside the range is stable. Out of the range is not stable. But if KP is equal to 10, so this is critical, where the KU occurred and omega U occurred. Okay, so we take this value 10, okay. This value, we call it as ultimate gain 10, put inside the even equations from the Routh-Lewis, which is here. Okay, 30 S squared plus 300 Kp equal to 10. So insert the Kp or K critical or Ku value, which is 10. Okay, insert the value and then you get the omega U. Okay, omega U, which is square root 100, which is 10 radian per second. Understand? Step number 3. Any question? Any question? Step number 3. Okay, proceed. And then step number 4 is to find the ultimate period, which is TU. Okay, as I told you before, TU is equal to what? 2 pi divided by omega U from the formula. Formula here. There. Okay. Then omega is equal to 2 pi f, okay, which is equal to 10, okay, the omega U. Then 2 pi divided by TU, okay, 2 pi divided by TU is equal to 10, okay. So TU is equal to 2 pi divided by 10, which is 0.6283, okay, save this value, all right. Then you use the tables here for PID, okay, 0.6 KU, TU divided by 2, and TU divided by 8. Okay, the value that you get here, TU and KU, which is this value 10. Okay. So insert the value. Okay, in these particular tables, so you get Kp is equal to 0.6 multiplied by 10. Kp is 6. Pi is equal to TU divided by 2. So 0.6283 divided by 2, 0.341. TD is equal to TU divided by 8. So it's 0.0785. Okay. And then from there, okay, you use this value, Ki is equal to Kp divided by Ti. Okay. So insert the value of Ti, you get Ki 19.1. Then Kd is equal to Kp multiplied by Td. So Td is here. So you multiply, you get 0.47. And then Kp is 6. So now you have the value 6 for Kp, 19.1 for Ki, and 0.7 for Kd. So you give this value to the technical assistant and the technicians. Okay, so that this value will be correct. Okay, and we can control the systems after you do the calculations. We don't expect the technical assistant and technician to know this because they don't learn degrees in electrical engineering. Okay.
Sir,
Yes.
I have a question here. Why did we multiply by 2 kp?
Why we multiply by 2 kp?
2 kp.
From here, Ki is equal to Kp is from these derivations, brother. From these derivations. Kd is correct, eh?
Okay, sir. Thank you.
From the calculations. Yeah. Okay, we have a break for 10 minutes. 10 minutes break. Okay, Assalamualaikum. Good afternoon. We continue the example of PID tuning using Ziggler-Nichols method. Can you hear me?
Yes, Dr. Ken.
Yes.
Now this is the second examples. Okay, again you are given the open loop transfer functions. Okay, unity feedback as usual, right? Okay, this is your output. So from this system is the third order. Okay, because the highest order of
Your
the
screen.
yes, Azira.
I cannot see your screen.
Azira, any question?
Yes, doc. You haven't shared your screen.
Oh, share the screen. Sorry. Sorry. Lupa. Okay. Bye. Right. Is the third order, and then is that one. Okay. So that one. Right. So usually, okay. So usually I see the root locus first. Okay. Root locus and time response. Okay. Shall we go and see the root locus and time response before we proceed for the Ziggler-Nichols? Is it okay?
Yeah, sure.
Okay. Dah lama tak main MATLAB ni. Okay. Right. So now you have a S, EF, bracket S. Okay. Then your open loop transfer function is equal to K, we assume as 1, 1, assume as 1, divide by S multiplied by S plus 1. Okay, guys. Plus, multiply by S plus 3. Okay. So that is the open loop transfer functions. Okay. So R locus, okay, R locus, open loop transfer function. Okay. Okay. So I share you the screen. Okay. Can you see?
Yes.
Okay. So we have 3 open loop poles. Okay. But now is 3 root locus paths as well. All are ended at infinity. Okay. All are ended at infinity. Just what do you call that? To get the critical gain from the from this particular plot. So usually I do some grid, okay, and then I change the properties, okay. Okay, so the limits I change to, instead of 12, I put -4. Then this one I make it 1, easy. Then this one I choose, maybe I choose 2, perhaps, so that you can see clearly. Okay, let me close. Okay. Then we want to see this point, okay, where Kc is equal critical gain. Okay, so critical gain is when the real is 0. So currently you see that the pole is minus 0.404 plus J 0.507 kan. So you have to scan this so that this 0.404 becomes 0. Only imaginary values. Okay. 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 Can you see that?
Yes.
Okay. What is the values of the open loop, closed loop poles there?
1.75i complex.
I call it J 1.73. J 1.73. I ini usually people are using iPhone, iPad, and they always use I. Huh? Right. Anyway, what is the critical gain? Adrian.
12.
Again.
12.
12, so PC is equal to 12, which is equal to KU. What is the value of the omega U, omega critical? Nurliana Izzati.
Yes, Doctor.
What is the value of omega critical or critical frequency?
Oh, 1.73 radian per second.
1.73
radian per second.
per second. Okay, so we close this one. Okay, we close this one, and then we go to the MATLAB again. Okay, to see the closed loop transfer functions. Okay, Nuraina Shafika. Nuraina Shafika.
Yes, doctor.
What is the closed loop transfer function?
Transfer function.
Equal to 1
over S
plus
3.
3. Mana ada 3?
Times S plus
S plus 3 kan? Okay, then plus 1. Betul. Correct. Functions. Bracket, not enough bracket over here. Nanti ada extension, double bracket here. Okay. See? Okay, so this is the closed loop transfer function. Why invalid?
Bracket.
Bracket, doctor.
Another bracket. All right. Another bracket. Third. All right. Okay. So the time response of the closed loop transfer functions without controller is step CLTF, closed loop transfer functions. Okay. So we want to see the peak time, the settling time. Okay. All right. So I share with you this one. Okay. Can you see? Can you see, guys?
Yes.
Okay. Right. So see the peak time first. Peak response. Over there. What is the peak time? What is the peak time, guy? Aina, Nabila?
8.86 seconds.
What is the settling time, Aina?
8.86 seconds.
Yes. Settling time. .8?
8.86. Settling time 10.4 seconds.
Telpel, what is the steady state steady state error?
Is it 0.03, doctor?
Wrong. The steady state error is 0, right?
Also 0, but isn't the peak amplitude?
Type 1. S then.
Oh, okay.
Okay, see the final value is 1. The input
Yes.
is 1. 1 minus 1 is 0.
All right, doctor.
The rise time, etc. Over here is 4.16. Okay. .16 seconds. Right. So we go to the iPad. Okay. Okay. So we already plot the root locus path, root locus and the time response. Okay. So we obtain Kc, which is equal to Ku is equal to 12. Am I right? Omega n 1.7 radian per second, which is omega critical or omega u. So since this system is a type 1, so the steady state error is 0. Okay, settling time 4.16, sorry, rise time 4.16 seconds, peak time 8.86 seconds, settling time 10.4 seconds, right? Then we move on to the Ziggler-Nichols alternate cycle method. Okay, by assuming KD, KI equal to 0. Why? Because we want to avoid the factor of derivative and integrations. Then we already given the open loop transfer functions, Kp divided by S plus 1, S plus 3. Then we find the closed loop transfer functions, and then we simplify this. Okay, so it becomes S cubic plus 4s squared plus 3s plus kp. So this part equate to 0, it become characteristic equations. Okay. And then this characteristic equation, these characteristic equations, okay, s cubic 4s squared 3s plus kp, okay, will be inserted to the Roth-Lewis tables to find the k criticals. So s cubic, s squared, s power of 1, and then s power of 0. Okay. So 1, 4, 3 kp from the characteristic equations. Then we obtain this one. Adrian, how do we get this 12 minus kp divided by 4?
3 times 4 minus 1 times kp over 4. Yang at S2, S power 2.
Negative kan? Negative 1
1 times kp
4
KR
divided by
4.
Yeah. Then same to this one, kp also same. Okay. Jumping around. Then from the root tables, okay. Column number 1. So column number 1 is positive 1, okay. Positive 4, okay. 12 minus kp divided by 4 greater than 0 and kp greater than 0, right? For stability. Okay. Sorry about that. Okay. Sorry. Right. Right. So this is the first equations, which is kp less than 12. Okay, from the first column. And then second equation, kp greater than 0. So 0 less than kp less than 12. Right? So if kp is equal to 12, what happened? Raja Ahmad Zahid. Tadi panggil tak nyaut. Raja Ahmad Zahid.
Yes.
Tadi tidur ke?
Apa ni?
Tadi panggil tak nyaut.
Oh, sorry, tak perasan saya.
Rasanya. KP is equal to 12. Is it stable or not stable?
Not stable.
Stable. Tak faham lah tu. Tak faham lagi. Nuraina Syafiqah. KP is equal to 12. Is it stable or not stable?
Critically stable.
Marginal stable or marginal critical stable. So that's why the gain of KP, the critical gain, KC or KP is equal to 12 equal to KU. Okay, 12. So we insert inside the even equation. Where do we get even equations? From the root ways here. Even equation. 4s squared plus KP. Okay. So insert the KP value, 12 inside here. Okay, so you get 12. Then the omega is KU. No, this one is KU. Okay. Insert the value. Okay, and then you get the value of critical is omega square root 3. Ni Umar square root 3, how many? Berapa?
The same with the MATLAB just now, it's 1.73.
1.73 radian per second, which is sama kan?
Yes.
Sama kan dengan apa yang kita dapat dalam simulations.
Yep.
From the simulations, KC 12. Calculation also 12. Omega C or omega critical or omega U 1.75 radian per second. So that's why simulation very important before you do the real things. Okay, simulate first. Okay, then from there you calculate the TU, which is 2 pi divided by 3. Okay, 3.6276. And find the KP, the KD, and KI from the standard table. Okay, which is here. Okay. So 7.2 for KP, TI is 1.8138, and TD is 0.4534. Then insert the value of the, find the KI and KD from the formula. Okay, KP divided by TI, KP multiplied by TD, so 4 and 3.26. Then insert this value inside the GPID, then you will get the answer of the controller. Okay. So that is the examples. Okay. So we go to the second tuning method, which is a Cohen-Kuhn tuning method. Okay. So after we look at the Ziggler-Nichols. So this method works well on the process where the date time is less than 2 times of the time constant. Date time, date time is usually we refer to the what do you call that? Time delay. Okay. Time delay is equal to date time, and time constant is tau lah. What is the definition of time constant? Ho Zhenghan.
Time constant is the time taken for the magnitude of the response to decrease by 0.637.
63%.
63%, yes.
Okay. Examples. Okay, so this is your response. This is your output. And this is your input, which is 1.0 volts. And your output is something like this. Okay. Okay. So this is output. This is input. Okay, the red is input, the blue is output, right? So time delay is this one. This is time delay. Okay. Okay, where the time taken, where the response start to what?
Increase.
Increase lah. Catching up. So this is time delay. Okay. So usually Usually the representative of it mathematics is exponent minus EDS. Okay? EDS. S is Laplace operator. Then the, what do you call that? Time constant. Time constant is 63% of the output. So meaning that 60% of 1 is 0.63. Am I right? Hello?
Yes. Yes.
Hello? Are you sleeping? 0.63, yeah? So this one we call it as a time constant. Understand?
Yes.
Paham tak? Edwin? Paham tak? Paham tak?
Yes.
Okay. So suitable for use for self-regulating process based on characterization of process by simple first order with the steady state gain K, time constant, and date time. Okay. In order to do this, we need a step response of the open loop system. Okay, has to be obtained. This response is also known as a process reaction curve. Okay, a step response of the open loop system, not closed loop. So the reaction curve must be cover the entire test period from the introduction of the step test until the system reach a new steady state. Okay. Typically, this will take a few minutes. Dia lambat, very slow. Okay. Or several hours. Okay. Depending upon the speed of the process. So that's why compared to the Ziggler-Nichols, it is different. Aggressive, meaning very fast. Okay. Cepat. Yeah. Pantas. So Cohen take a few minutes and it can take several hours. It's very slow. Okay, depending upon the speed of the process. So once the step procedure is carried out, okay, the process reaction curve is matched to a simple process model in order to determine the model parameters, which is the gain, which is the time constant, and which is the date time. Okay, so this is a first order plus date time, FOPDT model of the transfer function. So K is the gain. Okay, T naught, T naught is the time delay. Tau is what? Tau is time constant. Okay, in these equations. Thus, for a step change in the controller output of the magnitude, which is delta M. So we have these equations. Okay, these equations equal to delta M divided by S. Okay, where C is the output of the process. Okay. Okay. So GS is equal to CS divided by RS. So we give input RS. Okay. Step change maybe 1 volt, maybe 10 volt. Okay. Okay. So with the magnitude of delta M. Okay. So delta M can be 1 volt, can be 10 volt, can be 5 volt. So when we Laplace 5 volt, we get 5 over S. 1 volt, 1 over S. 10 volt, 10 over S. Something like that. Okay. Then multiply with the resistance. So the value of DC is given, shown in the figure below, which is a delta M. This is a delta M. Okay. Delta M, the magnitude of the step input signals. Okay. Shown in the typical process reaction curve, where this is the output and this is the input, the value of the step signals. This is the CS. Okay. So the step response, we below illustrate how the gain K, time constant, TC, and date time are estimated using a FOPDT fit method. Okay. So we have actuals, which is the real data. Actual is the real data. And model is the estimated data. Okay, so now you have two, actual and estimated. Okay, actual meaning you measure the data using a sensor. Okay, level or pressure, okay, or positions, you use a sensor. So if you want to measure positions, you use a potentiometer. If you want to use to measure the temperature, you use a thermocouple, or you can use other sensor, heat sensor. If you want to measure the pressure, you have to use the pressure sensor. So you get the values, the real values from the process. But estimated data is just what you call that as predicted. Okay, predict, estimate, model. All these are same word, which represent the model. Okay. So I show you there the time delay and the time constant. So this is a time constant, and the time delay is here. Okay, in between 0 and when the curve is going up. So to estimate T0 and TC, we can use one of the fit method proposed. This method uses the line that is tangent to the process reaction curve. Okay, tangent. At the point of maximum rate of change for FOPDT model, this happens to be at the K delta M 1 minus exponent minus 1, which is 0.632 delta CS. Okay. So the value of TC is one of the forces, the force the model respond to coincide with the actual response, which is T is equal to T0 plus tau. So an example of finding a date time and time constant is shown here is the first order system. Okay. So you have the time delay, you have the time constant, and you have the delta M and delta C, okay, shown in the slide 134. So it uses a formula, okay, same like PID. Cohen also have their own formula, which is here, okay, T0 and T tau. So it uses the value of time delay, the gain, and the time constants, okay, T0, tau, and K. See, this is a Cohen PID open loop tuning based on step response using a Cohen tuning method. Okay, so after that you insert the value here for the KC, for the TI, and for the TD. Okay, so some examples for you to show here, right? You are given a plot, okay, where K is equal to delta C, which is 0.6. Delta M is 0.5 volt. Okay, so divide, you get K 1.2. TD and T0 is the same, which is 1 second. Okay. Time delay 1 second, and the time constant is 1.8 seconds. Okay, it's given in the graph. So you use the formula for the output. Then you obtain the KP, TI, and TD using the table from here. Okay. Provided table is there. Then you get the GPID for the Cohen method, which is 1.8 for the KP, 0.9 for the KI, and KD 1.8. All right, so we already covered PE controller, PI controller, PD controller, PID controller, and tuning of the PID controller. So this is the end of the chapter 2 for PID controller, PID control design. And I will review some test question, past year test questions. Okay, test 1. So we will review maybe tomorrow or maybe next week. And then I already give you the slide for chapter 3. So I will begin chapter 3 inshallah next week. Okay. So tomorrow we will do some revision of past year test 1 question. Is it okay? Is it okay, guys?
Yes.
Yes.
Okay.
Okay, nak habis kelas okay. Faham tak faham? Wallahu a'lam bissawab. Right, so I guess it's time to end our lecture. Okay, so if you have any question, you can WhatsApp me personally, and I will try to answer. Okay, so I see you tomorrow, inshallah, 12 p.m. Is it okay?
Okay, doctor.
Okay.
Subhanallahi wa bihamdihi, subhanallahi wa bihamdika, ashhadu an la ilaha illa anta. Thank you very much. Salam.
Thank you, doctor. Walaikum salam.
Doctor.
Thank you.
Waalaikumsalam.
Thank you, Doctor.
Salam, Doctor.